Derating conductors of different sizes using Table 5 in Chapter 9 of the National Electrical Code does not eliminate the need to apply derating factors from Table 310.15b16. Table 5 provides adjustment factors for the ampacity of conductors when they are installed in a raceway or enclosure with other conductors. These factors account for the reduced heat dissipation when conductors are bundled together. Table 310.15b16, on the other hand, provides derating factors for conductors based on various conditions such as ambient temperature, the number of conductors in a raceway, and load diversity. These factors are applied to the ampacity of the conductor after any adjustments have been made using Table 5a. Therefore, when derating conductors of different sizes, it is necessary to apply the factors from both Table 5 and Table 310.15b16 to ensure that the conductors are properly rated for the intended use. Understanding the combined application of these tables is crucial for safe and compliant electrical installations. Firstly, Table 5 of Chapter 9 addresses conductor fill in a raceway. It provides the percentage of available cross-sectional area for different types of raceways and conduit bodies. This table is essential for determining how many conductors of various sizes can be installed in a given raceway without exceeding the maximum allowable fill. The allowable fill is based on the number of conductors in the raceway. Different percentages are given for 1 conductor, 2 conductors, and more than 2 conductors. Secondly, when using Table 5a, it's important to calculate the total cross-sectional area of all conductors to be installed in the raceway. This is typically done using conductor properties found in Chapter 9, specifically Table 5. The total area is then compared to the available area in the raceway, as determined by Table 4. To effectively use Table 310.15b16, firstly, identify the ambient temperature in the location where the conductors are installed. This temperature is a critical factor because higher ambient temperatures reduce the heat dissipation capability of conductors. Secondly, determine the number of current-carrying conductors in the raceway or cable. This is necessary because the heat generated by multiple conductors bundled together can significantly raise the temperature within the raceway. Thirdly, consult Table 310.15b16 to find the appropriate ampacity correction factors based on the ambient temperature and the number of current-carrying conductors. The table provides a range of correction factors typically expressed as percentages, which must be applied to the conductor's base ampacity. Once you have identified the correct adjustment factors from both Table 5 and Table 310.15b16, apply them sequentially. Firstly, adjust the conductor's ampacity based on the factors from Table 5a, which account for conductor fill. This step might involve reducing the allowable ampacity if the raceway is filled with multiple conductors of varying sizes. Secondly, apply the temperature correction factors from Table 310.15b16 to the already adjusted ampacity. This step further reduces the ampacity to account for ambient temperature and the number of current-carrying conductors. For example, consider a scenario where you are installing 4 current-carrying conductors in a raceway in an area with an ambient temperature of 40 degrees Celsius. The conductors are of different sizes, requiring the use of Table 5 to determine the appropriate fill. After calculating the conductor fill and adjusting the ampacity based on Table 5a, you must then consult Table 310.15b16 to find the temperature correction factor for 4 current-carrying conductors at 40 degrees Celsius. Let's say the table indicates a correction factor of 0.82. This means you must multiply the ampacity already adjusted for conductor fill by 0.82 to arrive at the final derated ampacity. This final ampacity is the maximum current the conductors can safely carry under these specific installation conditions. Remember that derating is a critical aspect of electrical safety and code compliance. Ignoring these derating factors can lead to overheating, insulation damage, and potentially electrical fires. Always consult the latest edition of the National Electrical Code and any applicable local codes to ensure compliance. The NEC provides comprehensive guidelines and tables to help electrical professionals properly size and install conductors for various applications. Furthermore, it's essential to consider other factors that may affect conductor ampacity, such as voltage drop and the type of load being served. Voltage drop can reduce the efficiency of electrical equipment and may require the use of larger conductors to compensate. The type of load, such as continuous or intermittent, can also affect the required ampacity of the conductors. Continuous loads, which operate for 3 hours or more, require conductors to be rated for 125% of the load current. In summary, Derating conductors involves a multi-step process that includes calculating conductor fill, applying temperature correction factors, and considering other factors such as voltage drop and load type. Table 5 and Table 310.15b16 are essential tools for performing these calculations and ensuring that conductors are properly sized and installed for their intended use. When working with conductors of different sizes in a raceway, understanding the application of Chapter 9 Table 5 and Table 310.15b16 is crucial. These tables address different aspects of conductor ampacity and derating, and their combined use ensures compliance with electrical codes and safety standards. Let's delve deeper into each table and how they interact. Chapter 9 Table 5 focuses on the allowable fill percentage of raceways based on the number and type of conductors. It's primarily used to determine how many conductors can be safely and legally installed within a specific conduit or raceway. This table is integral to preventing overcrowding, which can lead to overheating and insulation damage. Key aspects of Table 5 include firstly, raceway type. The table differentiates between various raceway types such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit, each with its own fill limitations. Secondly, conductor count. The allowable fill percentage varies depending on the number of conductors within the raceway. For example, a raceway with one conductor typically has a higher allowable fill percentage than one with multiple conductors. Thirdly, conductor size and type. The actual dimensions of the conductors, including insulation, must be considered when calculating the total cross-sectional area occupied within the raceway. Table 310.15b16, on the other hand, deals with ampacity correction factors based on ambient temperature and the number of current-carrying conductors bundled together. It addresses the issue of heat buildup, which can reduce the current carrying capacity of conductors. Key considerations for Table 310.15b16 are firstly, ambient temperature. Higher ambient temperatures reduce the ability of conductors to dissipate heat, requiring a reduction in their allowable ampacity. Secondly, number of current-carrying conductors. When multiple conductors are bundled together, they generate more heat, necessitating a further reduction in ampacity. Thirdly, ampacity correction factors. The table provides specific correction factors, typically expressed as decimals or percentages, which are used to adjust the conductor's base ampacity. The interaction between Table 5 and Table 310.15b16 is sequential and cumulative. Firstly, use Table 5 to ensure that the raceway fill is within acceptable limits. This step involves calculating the total cross-sectional area of all conductors and comparing it to the allowable fill percentage for the specific raceway type. Secondly, determine the ampacity of each conductor based on its size and insulation type, as specified in other tables within the NEC. Thirdly, apply the correction factors from Table 310.15b16 to account for ambient temperature and the number of current-carrying conductors. This step further reduces the allowable ampacity to ensure that the conductors operate safely within their thermal limits. Consider an example scenario. Suppose you are installing 6 current-carrying conductors of varying sizes in a rigid metal conduit in an area with an ambient temperature of 35 degrees Celsius. Firstly, using Table 5 and the conductor dimensions, you verify that the raceway fill is within the allowable limits for rigid metal conduit with 6 conductors. Secondly, you determine the base ampacity of each conductor based on its size and insulation type. Thirdly, you consult Table 310.15b16 and find the appropriate correction factor for 6 current-carrying conductors at 35 degrees Celsius. Let's say the correction factor is 0.88. You then multiply the base ampacity of each conductor by 0.88 to arrive at the final derated ampacity. It's essential to note that these tables are not interchangeable and address different concerns. Table 5 ensures physical space constraints are met, while Table 310.15b16 addresses thermal limitations. Neglecting either table can lead to unsafe installations. Common mistakes include, firstly, only using Table 5 and ignoring temperature derating. This can result in conductors overheating and insulation failure. Secondly, using Table 310.15b16 without verifying raceway fill. This can lead to overcrowded raceways, making it difficult to pull conductors and potentially damaging insulation. Thirdly, using outdated versions of the NEC electrical codes are updated regularly, and it's crucial to use the latest edition to ensure compliance and safety. To ensure accurate and safe installations, it's recommended to firstly thoroughly understand the NEC and any applicable local codes. Secondly, carefully calculate raceway fill using Table 5 and conductor dimensions. Thirdly, accurately determine ambient temperature and the number of current carrying conductors. Fourthly, apply the appropriate correction factors from Table 310.15b16 sequentially. Fifthly, double-check all calculations and consult with a qualified electrical engineer or inspector if needed. In addition to these tables, it's also important to consider other factors that can affect conductor ampacity, such as voltage drop, harmonic currents, and the presence of nonlinear loads. Voltage drop can reduce the efficiency of electrical equipment and may require the use of larger conductors to compensate. Harmonic currents can increase conductor heating and may require the use of derating factors or specialized conductors. Nonlinear loads can generate harmonic currents and may require the use of harmonic filters or other mitigation techniques. The National Electrical Code is a comprehensive set of guidelines and regulations designed to ensure the safe and reliable installation of electrical systems. It's essential for electrical professionals to stay up to date on the latest code requirements and to follow best practices for conductor sizing and derating. Remember that electrical safety is paramount, and proper conductor derating is a critical component of ensuring a safe and compliant electrical installation. By understanding and applying the principles outlined in Table 5 and Table 310.15b16, you can help prevent overheating, insulation damage, and potentially electrical fires. Always prioritize safety and consult with qualified professionals when in doubt. The correct application of derating factors is not just about meeting code requirements, it's about protecting people and property from the hazards of electricity. Always take the time to perform accurate calculations and to verify your work to ensure a safe and reliable electrical system. Furthermore, consider the long-term implications of your installation. Properly derated conductors will not only operate safely but will also have a longer lifespan, reducing the need for costly repairs and replacements. Investing in quality materials and taking the time to perform accurate calculations is a wise investment in the safety and reliability of your electrical system. When faced with complex scenarios or unfamiliar situations, don't hesitate to seek guidance from experienced electrical engineers or inspectors. They can provide valuable insights and help you navigate the intricacies of the National Electrical Code. Remember, electrical work is not a do-it-yourself project. It requires specialized knowledge and training. Always hire qualified professionals for electrical installations and repairs.